Okay, so I think I had been confusing some. Sorry. Okay. Hey, how's it going? So I think some of my prior videos. Uh, okay. Okay. So I think some of my prior videos, I left out a couple of important parts, and that might have been leading to maybe some questions or confusion. So we want to look at this idea of line fitting, and we're talking about using light. And the idea behind what is a line, what is a basis function. So what we have here, what we're looking at here is an example from Desmos that basically shows a whole bunch of points, okay? Now, I can go on and I can try to fit this by hand, right? So I can change, so what is H? H is, because the way Desmos uses things, I couldn't call that R for rise because I needed R for run. So I figured, well, rise is just height, so we'll change in height. So H is just the change in height. So dy, so again, remember slope of your line is rise over run, dy by dx, right? So h over r is rise over run. B is just the point at which it intercepts the y-axis, right? And so what we are saying is that this point y, which is a point in the upward direction, right? So we're trying to define a thing on the y-axis by defining how to get to that point off the x-axis. That's why we call this a transform, right? So we basically measure a whole bunch of different quantities, and if we measure a particular quantity at just a little more than half, and we make one measurement and we get, say that we make, I don't like how this, so let me just rearrange the data here so that it's a little bit more exact. Because I want this to sort of make sense. And so let's do it this way. Okay, so in a histogram, remember, the thing that we are measuring, the measurements that we get are scattered on the x-axis, right? So if you have a ruler, and that ruler is 12, let's go with the meter stick, right? So you got 1 meter, and you measure something to be at half a meter, and you make another measurement, and maybe it is at 0.75 of a meter, right? 3/4. And then you make another measurement that it's somewhere in between half and 3/4. That means that your points will be distributed near your measurement, right? So what you might look at and you might get with your measurements might be something like this. This is a bell curve. But for now, let's just assume that when we take our histogram, we haven't found the lower limit, right? So we found every time we make a measurement, we get closer and closer to getting 5, but we get fewer and fewer near 0. So we make a whole bunch of measurements. More of our measurements are at 5 than they are at 0. Okay, and what we want to do is, so remember that the height here is just the number of times that you've found that measure, right? So you take all your points, you make your measurement, you write down all of your different measures, and then you group together the measures and how close they are. Let's not worry about bending. Let's not worry, is 0.51 the same as 0.5101? We're not worrying about that at this point, okay? So right now, it's just you make 100 different measurements, and you look at the measurements, you look at your degree of precision for your measuring device, and you use that to tell you what your bend width is, okay? Let's not split hairs trying to figure out what bend width should be at this point, okay? That comes down the road. So you go and put all your points, and they form a line on the graph, right? So, or maybe it's not a line, maybe it looks like this, where it's not necessarily a line. So what do? We basically start at the 0 point, or maybe you don't start at the 0 point, and you try to fit a line that goes from one point to the next, and then you try to fit from that point to the next, and then from that point to the next. But the problem is that if you do it this way, number one, it's what's called overfitting in machine learning. Number two is it's really hard to describe an equation that way. So let me explain. So we have all of these different points here. If I wanted to describe each of these points, the easiest way for me to describe these points is in terms of a basis function. The basis function simply is that you have a point along the x-axis that's not 1. That's not 0. Okay, so it's just 1. And then you'll have another basis function, or you can use a transform to, but the point is that you have basically a set of points that basically knock out the values that you don't have. How can I? So I think a better way of maybe picturing this is, let me add another expression here. Let me say that y is equal to sine of x, okay? So now here, every single point that is on this graph, right? Because it's continuous, right? But if we just consider it discrete, just for the moment, and I multiply this by sine of x again, right? We get basically the square of the function, right? But where it's 0, it stays 0. But if I shifted this by 90 degrees, everything is still perfectly fine, right? But there does come a point where, let's see. Yeah, sorry, that's what I was looking for. I was just trying to force one of these to be 0. Okay, so if one function is 0, the other function is completely dead across the entire space, right? So if I can make this a function that only exists at a certain point, so exponentials are great for this. E to the minus 5 minus x, and we square this. And let me make this h. See? See what's happening now? Ignore this line. Look at what's happening here. Is we are seeing, so if I get rid of the sign, what we see is the Gaussian function moving left to right. So right now our basis would be around 10, and it would be pretty wide. It would go down to, what is that, about 8 on one side and on the other. So our basis function, one of our little points here, okay, I explicitly put that under the bell curve for a reason. Hopefully it'll make sense in a couple classes from now. But if I flip that, did something like that, with your background in physics, looks like a potential, right? How we typically draw Einstein's relativity. Yeah, there's a connection there. Okay, so basically, that's your basis function, right? So if you have a lot of points in this area, this is why I was talking about the width, the size of your basis function actually mattering, right? So I can come up here and I can say that this maybe is R. So I can adjust R to handle the width there, right? So as I change R, you can see the width changing. As I change H, I can change the position. So if I have more and more data points in here, and let's say that this point is right here, then I can change this to be a bit wider, a bit broader, right? So the wider it is, the more uncertain, because remember what we talked about with distributions, right? So, but if we had just a single point in our data, so maybe all our data was just wrapped around this point, then we could have a very sharp Gaussian, right? So that's the idea that we're trying to look at here, is what I'm trying to get across is that each one of these is its own Gaussian. So how do we know this? Because I can do this. This one might be B. There we go. We got two different points on the line. One is negative. I can fix that. Okay, so I got one popping up somewhere around here. The other one pops up around 10. Now, if I take this function and multiply it by a line, then what I expect to see is what? We have a function that's zeros everywhere except for 2 points. So what should I expect? What should I expect happens if we multiply those two together, right? I should expect that the value at those 2 points, which is just 1, will now become the value of whatever the line is at that point. So let's take our equation of our line here, and I'm going to have to change this to this and to this. Okay. Yeah, perfect. Okay, so that's our line, right? So what do we expect our new equation to look like now if I multiply this by the other one? It should look like a staircase, right? Sort of. Let's see. So let's try it. So here we do expression. So I can do y is equal to, oh yeah. So I gotta say that this is like y0, and this is y1. So this y is going to be y1 times y0. There you go. Basis functions, building blocks. So I created now a line. So I created now a function that represents both other functions. It represents the line and it represents the initial basis function. Why? Because the two basis functions have been scaled by the form of the line. So that now the line intersects, the basis functions have been scaled to intersect the line. And if I change the slope of the line, look what happens. This is why we say structure from geometry and structure from information. These two lines, if you think about this from your physics point of view, and you put a center of mass here, then you can work out the torques, and this is exactly what's happening. These are acting as an impulse force on one side or the other of a line. So I can pull this down like this, and there's your geometric representation of torque. When we look at functions in the math as being more physical than just simply arbitrary numbers and points on a line, it really can help us understand how the world works. So now I've shown how to do this, right? So now we can come back down here. Oh boy, I erased all my points here. Shoot. So maybe this should be like y10. And this one should be like y20. And I got my data points back. Beautiful. So again, what we are saying is, if we were looking at a histogram, maybe we have all our measurements like this. Okay. So that would be basically going from here to here. So again, when we create this new function, we're getting the basis points, we're not getting the arbitrary line in between. Why? Because the arbitrary line in between is pointless. Nothing exists here. I made it exist by this equation. Okay, so when we're trying to curve fit our data, what we are going to do is basically, let me get rid of these now. I can basically try to work through this. And I can try to go from this point to this point. And like I said, we can make all of these points here, but that's not really the best thing because we don't have every point between these. So really, we just want an average line. So what do? We look at the height from this point, initially maybe to this point. That change is going to be roughly 6 minus 2, so that's going to be somewhere around 4. So we make our h around 4. Look at that. Perfect slope, right? Because it's 4 divided by, what is this, about, that's probably like 4.5. Yeah, so it's a slope of 2. That's what we have for r. So now the only thing is we're off by our intercept, and bam. Okay, not really the best fit, but but without using a calculator, perfect, right? So let's see. And then you would want to do this line to this line, and then so on. But interesting thing is that a lot of times, not all the time, you can basically look at the average of all the points. And this is where you have to be careful, because you have to set your y-intercept, because that it matters on how well you want this line to be structured. So yeah, so that gives us an average line. But what happens if the data is something like this, right? Something a little bit more like this. Do we have to start over with x squared? No. What we do is we just make a higher order approximation. So we take our original x and we add another x. So we make it x squared. And then rather than this being h1, h0, we're going to call this one and this one. And now you can see if I zoom out. So unlike the first time, where we were only working with the parabola, see, I can actually move this around, and so I can take this and this should go out to 100. And there, okay? I could tighten it up a little bit more too, but so that's one way. Another way is, well, what if I don't want to move the thing to the left? Well, then I can just do this, h3, h2 divided by r1, h2 divided by r2, it's xxx, and, oh, no, I lost the thing, okay. And now, I want to bring this back to the center where it was. And now I can manage to adjust the others and okay, so you can see here that I just need to scale this a little bit more that way. So the run, if I scale that, this is the hard part, is that we now have to keep scaling these. So we scale this. Okay, this is going to fight with me all day. Point is that I'm trying to get across is this x plus xxx plus xxx gives us this, and h2 r2, and I'm just randomly putting these things here just to make a point. Okay, so okay, yeah, I'm really gonna need one of this. So I need to shift the mean h2. No, let's just say h. still scaling it in the y. Okay. Well, I'll put a note to fix this later, but the point is, you should never, ever, ever do this. But I'm just doing this for the sake of the point that I was trying to make. So we can imagine if I could figure out how to broaden that well, which is somewhere along one of these terms. Maybe it's because it's not really x squared. Maybe it's more like, maybe if I had done like x to the 1/2, x to the 1.2. Yeah, see, that's how you broaden it. You change the exponent. So again, nothing I was trying to get so tricky with the fitting and everything, but so hopefully that explains everything a little bit clearer, why the basis functions matter. And now we can do something really cool. So I can take this new equation that I just worked out and say what happens. Why did I do that? Come down here. So what this is doing now is it's multiplying this equation, which we worked out earlier, and it's multiplying it by the little equation that we worked out here. So this is why, again, so here it doesn't make any sense to have our basis function here, right? So which one was the basis, second basis function, h b. Yep, there we go. Ha. Okay, so why basis functions and other higher order functions are useful, especially when you multiply them together. Okay, thanks.